Okay, so this topic is actually one of the reasons why we took such a I mean, random walks are also obviously related to randomized algorithms. But one of my goals is I realized, oh, actually, you guys are not that far away from understanding a lot of the proof of this result, which is really one of the highlights of TCS. So, um, right, this is just some of the random walk stuff we've been doing, and I guess you're doing homework now indefinitely. Um, right? Last time so we did all this stuff with expanders and random walks and stuff. Right, here's what we did last time. We were doing this error amplification, but with fewer random bits by using the expander to generate the next samples. Um, and we did a proof of the Chernoff bound. Okay, so today we're going to do something cool. It's called probabilistically checkable proofs. So it's really a randomized spin on this P versus NP question. So this you've seen before, but I'll just remind you. Polynomial time means there's a deterministic polynomial decision algorithm. Give me X, I'll tell you in polynomial time it's in X. It's in the language or not. Okay. NP means not that there's an algorithm to decide it, but there's an algorithm to verify membership in polynomial time. Okay? Or a proof of a membership. So then you have this sort of algorithm that takes two inputs, your original input X, like a graph or something, and then a proof Y, an independent set of size K or something. And there's some polynomial time verifier that can look at X and Y and use that to verify that X is in L. Okay? So that means that if X is in L, there is some Y that will make the algorithm say yes. If X is not in an L, for any proof, you will not convince me that X is in L. Okay? So, good. All right, so this is the model we'll look at today. Okay, so the class of PCPRQ. Okay, so here's the idea. You're looking at proofs. They may be big. Okay, but the question is, do you have to look at the entire proof? Okay, so the idea is that you're allowed a certain number of random bits and a certain number of queries. So based on the random bits, I'll look at the first slot and the 100th slot and n minus 5 or something. And I'll only look at those bits of the proof and make up my mind. Okay? So the proof may be long, but you're only going to access small parts of it. Okay? So the class PCPRQ is the ones with these kind of verifiers. So the verifier is going to be given, the X, that's really what you're asking a question about. And then this oracle access to Y. Okay? And it's going to look at X, and based on that, it's going to make Q queries, using R random bits. And for us, actually, it won't be adaptive. So it'll just look at X and then decide what to query, as opposed to querying, finding out, choosing your next query. Uh, oh, sorry? Yeah, I guess just as a rule, we're assuming Y is polynomial then. Okay. Good. Uh, well, we're doing this oracle access thing anyway, so we're doing, it could sort of fit in this orc. So you're just wondering, it's a little bit more of an information theoretic. How many bits do you need to look at the proof to be able to say something about X? So, okay, you're going to choose your queries and then you're going to make them. I've only separated in two steps to emphasize that it's not adaptive. So you decide just based on looking at X, and you can spend a long time looking at X, where you want to query. And then you look up the bits. And you look up those Q bits, Q queries. I don't know why I wrote big O Q. It could be just Q. And then you decide whether to accept or reject X. Yeah. I don't have a great answer for you, but I know that So a PCP that is adaptive would only be stronger. But we are going to be able to show that something falls in a non-adaptive class, which is just stricter. So I guess the direct reason is because we can get away with it and it's stronger uh, to say that it's not adaptive. Um, but adaptive could also be interesting. Yeah. So a little arbitrary. Okay, so well, okay. So if you didn't have any random bits, then what's the point? Oh, okay. Maybe it'll make more sense in a moment. So I haven't talked about like the guarantees. So here's the rule: if X is always in the language, you should always accept X. Okay, so no false negatives. And if X is not in the language, then you should accept with some bounded probability, say at most 1/2. Okay, so with our no random bits, then there's no possibility of error here. Okay. So in general, if we didn't have any randomness or anything, it might get really hard because then you're basically asking for really really small proofs. Just qubit proofs. Yeah. So I think the idea is that part of the idea is that the proof should be pretty good, but it needs to be robust, right? So in other words, it's sort of like the verifier is going to try to query something to try to find mistakes in your proof. It's only going to look at 3 bits or something, right? And if all 3 of your bits look good, it'll just accept. But if it finds a mistake, then it'll reject. So it's asking for like a very robust proof. Yeah. Yeah, well, if it's polynomial time, it's only going to use a polynomial number of random bits anyway. But there are people who want to figure out how many random bits you need. Like what we did last time, we were trying to reduce the number of bits on amplification. That's from the pseudo-randomness space, where the goal is to get all the way down to 0 for all problems, which you don't know how to do, but there's some effort to get lower. Yeah. Good, good. So like, what would be a real life example? I have a very good example. Uh, Very close. So some of you are teaching assistants, right? And then you grade finals and word problems and things like this. And if a solution is correct, you can almost see right away. And if a solution's wrong, it's usually wrong all over the place, right? You just choose 3 random parts and you realize, oh yeah, it's wrong. So you can almost do homework grading and exam grading with, some scheme like this. You don't have to really look at all of the I guess this includes you, but some of the answers, like the handwriting gets really small and it starts sloping off of the page and like this, right? And it's like, okay, you don't have to look at it too closely and you kind of sense. Okay, so that's the joke. You can use the PCP theorem to grade homework. But what it's really asking is there like a very robust proof system, okay, where uh, the only way to really prove something is where all the bits are correct. Okay, so good. All right, so here's the big theorem. The big theorem says that for any MP problem, you can come up with some kind of probabilistically checkable proof system where you only need to make a constant number of queries. Okay, the log n bits is just to choose the indices for your queries. So you only need to look at a constant number of bits to decide things with constant probability. Okay, this is very strong, right? Um, and the corollary is eventually leads to uh, the proof that for all epsilon greater than 0, 7/8 plus epsilon is APX hard, is MP hard. Okay. So one way to think about it is this: let's say that you're trying to do a PCP for SAT, right? Let's say 3 SAT. So is this formula satisfiable? And you get some assignment, right? And like, what's like a randomized way to try to check if the thing is correct? Sample a random clause, and if it's wrong, it's definitely wrong. You say it's wrong. If it's right, you say, okay, maybe the whole thing is right. Okay. But the only problem is if there's only one mistake out of m, you're often not going to find the mistake, right? But compare that to this stronger version, right? Where getting between 7/8, trying to get more than 7/8 of them correct or none wrong. Like it's like saying there's no difference between 0 error and up to 1/8 error. Okay. So, uh, okay, so let's say that you wanted to verify this problem. Okay, so you're given a formula and you want to know if it's 9/10 satisfiable. Or no, you want to know if either, okay, given a formula, you want to know, like I'll give you some like margin for error. You want to know if either it's satisfiable exactly, or the best you can do is at most 7/8. Okay. How might you try to verify this? Okay, no, let me put it this way. Okay, I'll give you double-sided error. Suppose I said that, okay, if the formula is satisfiable, you should say yes. If you can't do 7/8, you should say no. If the formula is anywhere in between, you can say whatever you want. So you only have to be correct if it's exactly, I mean, right about the answer if it's, opposite ends of this gap. So you have this massive margin for error. Everything between 0 and 7/8, you can say whatever you want. That's like a murky thing. How would you come up with a probabilistically checkable proof for this? You check a random clause. But now, if at least 1/8 of them have mistakes, you have a constant chance of finding it. Okay? So you check a clause. If it's correct, you just say it's correct. If it's incorrect, you say it's wrong. Okay? Now, uh, if you say it's wrong, I mean, if you notice it's wrong, it's definitely not satisfiable. So that's good, right? You don't, as long as it's not satisfiable, you can say no. Now, you do want to make sure if the formula has at least 1/8 error, then you say no with 50% probability, right? So if it's a 1/8 error, you have a 1 in 8 chance of actually getting one of the bad clauses. Okay, so you won't quite get 1/2 probability. You'll get 1/8 probability, but how can we make it better? Yeah, you just do it a constant number of times. Okay, so you can see why this one might permit, and you can start to see some of the connections between the original PCP theorem and the 7/8 system, right? The 7/8 thing is somehow saying that getting better than 7/8 of them correct is the same as getting all of them correct. All right, so good. And it leads to basically a lot of hardness of approximation problems. Like for example, we did set cover, right? That's log n, and we know you can't do better. I think we know that you can't do better than log n unless p equals np. Could be wrong, but I think that one we also know the hardness. So there's many problems where we know that you actually can't get arbitrarily good approximations. We already knew they were NP hard, so you can solve them exactly, but there's also limits to approximation. Okay. Good. All right, so that was about equality. So let's try one direction. So uh, just to play with some definitions. Okay, so I'm claiming this direction is a little bit easier. The claim is that the class of problems with that can be verified with constant number of queries is contained in NP. Okay, so if I give you a problem, I don't know if you can, if this is too small on the right, but if I give you a problem in PCP log n1, then we can show that it's in NP. So let me zoom in on the right for you. Okay, so I think that's the right intuition. So we need to come up with a verifier and a polynomial size proof. Yeah, yeah, yeah. So we can use the same proof that the PCP is using, this robust proof, okay? And the verifier can try all possible random strings and do it and see, if it's at most one half or something, right? Okay, so you can just try all possible random strings in a loop and then fit it to the definition. Okay, so I think this is at least one reason why it's convenient to just assume that the proof was in polynomial size for the PCP. Um, but also, yeah, so there's an earlier point of like in PCP, why do I require the proof to be polynomial size? Well, I guess at least in this context where you have log n random bits anyway, you're only going to query 2 to the log n possible different places over all possible random strings. So you might as well just use those polynomial locations for the proof. Yeah. So, okay. Good. Okay, so the opposite direction is harder. And our construction is going to sort of start with a simple problem like 3 coloring a graph, and then it's going to get a little bit more involved to what are called graphical constraint satisfaction problems. Okay, so graph coloring, you just have a graph and you want to color it. Okay, so even to decide if so that node edge has the same colored endpoints. Okay, now even for 3 colors, this problem's NP hard. What about 2 colors? It's just bipartite graph, right? So 3, magic number 3 is hard. 2 is easy. So we'll just start with that, okay? And we're going to generalize it where at some level, instead of like, we can think of them as as colors, but we're going to kind of like be assigning letters to every vertex from like a mildly large alphabet to some constant size. And each edge is going to be associated with like some kind of formula that only accepts certain combinations of letters. Okay, so in graph coloring, the letters are the 3 colors, and the edge only accepts the endpoints if they're different colors. But in general, you can make like a whole table of things that get accepted and not accepted, and so that's called graph CSP, constraint satisfaction problem. So good, right? So okay. So before the graph part, let me first just explain what a constraint satisfaction problem is. So you have variables, an alphabet, and clauses. And a clause will consist of k variables, q variables, q variables, okay, and a subset of good combinations, right? The things that satisfy the clause. So this could be some small computer program that does a loop or something. Who knows? Could be a stat formula. Good. And what's down here? Oh yeah. So a simple example is graph coloring. Okay, where each edge represents a clause. Now, just some notation. I guess given one of these problems, I'll write unsat to be the minimum fraction of unsatisfied clauses possible, right? So it's like opt, but you're focusing on what's the minimum you can miss as opposed to the maximum you can satisfy. Okay. And it's relativized between 0 and 1. So 0 means satisfiable. So just distinguish between 0 and non-zero is NP hard. Sorry, 0 means satisfiable. That's right. There, yeah. Okay, so good. Um, okay, so all right, let's consider this theorem. So the claim is that there's integers, finite numbers. Okay, so for some finite q, finite alphabet size, and this is the theorem we're going to try to prove. It's NP hard to try to decide if either unsat is 0 or unsat is at least 1/2. Okay, so to decide if either all clauses can be satisfied or if at most half of them can be satisfied. So as opposed to doing 0 or non-zero, there's now a gap. Okay, so I can promise you that the input is one of these two, and you have to decide which one is which. Okay. Um, and the claim is that this is NP hard. This is the thing we're actually going to prove directly. Okay. So this is pretty similar to SAT, but we want slightly more degrees of freedom because we're going to do some crazy auxiliary stuff and stuff like this. So instead of we won't necessarily be as clean as a SAT formula, things like this. We just call it a CSP. So we want the degree of freedom for the reduction. Okay, so it doesn't have to be an exercise because we don't have any homework left. It used to be an exercise. So maybe we could still try to think about this. So the claim is that this sort of half or nothing CSP problem is equivalent to PCP theorem, where here I got this backwards. Okay. So what would be the connection between these problems? Maybe it's direction easier to start here. So suppose the theorem was true. Suppose it was NP hard to decide 1/2 or 0, right? That means for any NP problem, I should be able to come up with a probabilistically checkable proof. Well, okay, maybe even for starters, what would be uh, what would be a PCP for this half or none, half or perfect CSP problem? Yeah. So sample, I guess they're called constraints here. But just like we did for SAT was a 7/8 SAT, 7/8 or none kind of thing. Just try a clause, any random clause, and if more than half of them are errors, then you have a 1 in 2 probability of finding the error. Okay, so that's already a problem. We don't even have to repeat for this one because it's already 1/2 for us. Okay, so that's a probabilistically checkable proof for this problem. Now, what if you're given any generic NP problem? Probably the more interesting ones are NP hard. So say like independent set. So PCP claims that all problems in NP have probabilistically checkable proofs, right? So how do I come up with a probabilistically checkable proof for independent set? Yeah, yeah, that's right. Yeah, so if you remember what NP hard means, that means I can take independent set, which is there an independent set of size k or not, and turn it into this problem, and then use the PCP on that problem. Okay, so once you can do the right-hand side, then you have PCPs for all problems in NP. Okay. Now, okay, good. So you're getting some intuition. Now the claim is that they're equivalent. So what about the opposite direction? So NP hard means it can solve any problem in NP. NP means that it has a polynomial time verifier. And then, that's right. And this is clearly an NP because you can just check all the clauses and see if half of them are satisfied. But what you really need is NP hard. Okay, so now the opposite is, suppose NP is equal to PCP. So all problems in NP have a probabilistically checkable proof. Okay. Then we claim that that this sort of half or none constraint satisfaction problem is NP hard. Okay, so if all NP problems have a PCP with constant number of queries, then we claim that the CSP problem should be able to solve it. So we should be able to take the CSP and come up with some constraints and stuff like that. Yeah, so every random bit string should become a clause. Yeah, should be clauses that should be looking. You should figure out the bits corresponding to those the query bits. So for every possible random bit string, you figure out the query bits, and you make a CSP. Depending on whether the verifier would accept, or which of the bits, which of the inputs for those possible queries would make the verifier accept. So you flesh it out a little bit, but basically you're going to get one clause for every random bit in the PCP, and to decide which of your inputs satisfy the clause, you should look at which of the answers to the queries would have made the PCP happy, right? So the PCP has some proof, it has access to. It looks at, it gets some random bits, which gives it a certain number of places to query, some constant number, and then it looks at some bits, right? Oh, that's a 1, that's a 0, that's a 1. And then it decides yes or no. So there's some answers to those queries that would have made us say yes, some answers to the query that it would have said no. So the ones that would have made us say yes, that's what you want to use for that particular constraint. Okay? And the variables in the constraint will correspond to those bits, locations of the queries. Good. So these two are equivalent. You can flesh it out more slowly at home. And now we just want to focus on this theorem and try to show it's NP hard, for this CSP with a gap. Okay. And here I think 1/2 can be any constant, because then afterwards you can just take sort of like powering, like combine a bunch of constraints to get your error up. But anyway, I'm not sure if we're going to get all the way to 1/2 or not. I don't quite remember. We'll find out. Well, at least show a constant. Yeah. Well, I guess we argued they are the same, ultimately. Um, I think for our proof, the right-hand side is more concrete. I guess what we're about to do the proof setup. Like the left-hand side, how can you show that any problem in NP has a PCP with constant queries? Like, where do you even begin? The right-hand side is sort of where we're going to begin. We're going to just focus on this generic problem and trying to show that getting 1/2 error, 50% error is NP hard. So I guess, yeah. So maybe it'll make more sense in just one moment, right now, actually. So, as mentioned earlier, a simple case with just two variables is graph CSP. Okay, so every variable is a vertex, and then the edge between them represents a constraint. Okay, and in graph coloring, the letters of the constraint problem are just colors, and the edge constraint is just checking if the colors are different. Okay, so that's going to be our starting one, right? So for graph coloring, we don't have 1/2 or 0, right? But we do have something versus 0 is NP hard. What would that something be? Yeah. Yeah, or just 1 over m. Distinguish between 0 error or relatively 1 over m error is NP hard because that's just no mistakes or one mistake, right? So we have a starting point. We have an initial problem, and the only issue is that that gap is too small. So we're going to try to take that 1 over m and put it on steroids. Okay, so we already have this to start with. So we have a graph CSP where it's NP hard to distinguish between 0 and something polynomially small. And we want to try to take that 1 over m and ramp it up to a constant. I don't even know how to respond to that. Okay. 1 over m is relative. Yeah. Well, congratulations. Okay. So here's what we're going to try to do. Okay. It's going to be pretty cool. So first, we're going to make the graph a constant degree expander. Okay, we're going to make the graph a constant degree expander. And then, okay, so what we're going to do is something that's sort of inspired by graph powering, but it's a little bit messier because, so the underlying graph will be powered, but then the letters of the alphabet are going to change. You're going to have to define constraints, over those kind of walks and stuff. So it's going to be a bit more involved, but it will be like graph powering. And yeah. I guess we'll find that out in a moment. Because probably first step 1 is going to come very close to that. Because we'll just make it an expander. But it won't quite be graph coloring. And then, so what's going to happen, it will make more sense when we do the details, is that the powering is going to end up increasing the size of your alphabet. Okay, so we're going to do some kind of powering that's going to help increase the error. Okay, but it's going to, it'll make more sense when the details come out. It's going to increase the size of our alphabet. So that becomes an issue. So we're going to have to reduce it. Okay, and then the cycle continues. So, sorry? The what? Yeah, the colorful color. Yeah, so it's obviously very similar to stuff we've been doing, but it's not going to be. It's a little funky because we're not just taking a graph and shaping it the way we like, but we have to also maintain a CSP. So we need to like redefine alphabets and redefine constraints and things like this. But absolutely some similar intuition. Yeah. So I think this comes after deterministic log connectivity. It was clearly inspired by deterministic log space connectivity. Okay, so but I mean the PCP theorem is from 92, 93, 94, and this proof is from 2007, 2006. So this comes later and is much cleaner than the original one, which I really haven't read through at all. Okay, good. So, all right, this one you guys might be able to guess. So I have a simple graph CSP, and I want to make it a constant degree expander. So A, I want to make a constant degree, and B, I want to make it an expander. Maybe we could focus on constant degree first, but what are some ideas? Ah, okay, so we can just take a vertex and split it. So if I take a vertex, uh, right? So this vertex is in various CSPs, and the idea, I mean, each of these edges represent a constraint, and the idea is uh, we split it up into three constraints. I mean, three vertices, which one for each edge or something, right? And maybe add some edges in between. Now we have to decide what the constraint will be on those auxiliary edges. Ah, equality. So I just say, okay, whatever you assign here has to be the same as what you assign here. Okay. So good. So that's basically what we'll do. Now, one thing we want to do. So imagine, okay, I only drew three here, so it's also a complete graph. But if I drew a bigger one, was like, you know, very large amount. Now, we're not in the regime of all or nothing error, right? So all or nothing error, you can't make any mistakes. So just having a cycle over the auxiliary vertices is good enough. But we are going to, we are actually care more quantitatively about, you know. So we're going to add a few extra edges in between, okay, to robustify it. But we don't want to add too many edges. So what's a graph that's sort of like very well connected, but doesn't have many edges? It's exactly an expander. Okay, so rather than just a cycle, we're going to put some constant degree expander as the auxiliary thing. So I'll take a vertex, split it up, and try to add a few edges, but enough edges so that on balance it should want to be equal. So there should be enough connections that you still want to make everything equal. Okay, so good. So that will address the degree, but how do you make the entire graph an expander? Actually, the way we're going to do is actually simpler than you might think. Yes. Well, they should do something. Okay, so we are just going to add edges on top. But if I want to turn the whole graph into an expander, what should I add on top? Far away things, but how can I kind of guarantee that? Like think of it, okay, I have my original graph and think of putting another graph on top. What should that other graph look like? An expander. So we're just going to generate an expander with the same number of vertices and throw it on top, and now it's guaranteed to also have good expansion, right? All the cuts will be big and things like this. Okay, so yeah, this is actually kind of crude, but it's going to work. Okay, so good, equality constraint. Yeah. Oh, I guess it's two steps. So, okay, for what it's, let me just mention this. After the degree splitting was an expander, the number of edges doesn't go up too much because first splitting doesn't increase edges. And then you're adding an expander that, uh, you know, each vertex is going to have three new edges or something, right? Auxiliary vertex. So number of edges is only going to go up by constant. And now you're going to have a regular graph that's constant degree. And you can show, in part because of the expanding and the strong connections, that unsat only changes by constant. Okay, this is not too bad, so it's left as an exercise. Many parts of this lecture will be left as an exercise compared to usual because it's a bit involved. Okay. Equality constraints, like you suggested. Oh, that's what you're saying? Yes. Yeah, one sec. Where is I feel like I'm missing a slide because I didn't talk about there's nothing in the slides about slapping the expander on top. Okay, good. So you put the expander on top, right? So we not only do you add edges, but you need to define constraints for those edges. So what should you do? So you don't want these edges to be very consequential, right? Because they're kind of arbitrary. Yeah. So we're going to add a trivial constraint. Any endpoints are okay. You always satisfy this clause. So it'll change the graphical properties, which will be useful. But it won't change really it'll be easy to satisfy. Now, remember, we're trying to get unsat up to like a constant. So in this regime, unsat is very small. So you're gonna make unsat a little bit lower, but it's gonna be okay. Yeah. Okay. Good. So right. Okay. So you're gonna add some easy clauses, right? So it's gonna look like you're satisfying a higher fraction. Things will go down by a constant, but you're adding a constant number of edges, so it's okay. Or constant, yeah. Okay, so good. So that second slide, I don't know where it went actually, but that's okay. Okay, so that's the first thing. How do you turn G into a constant degree expander with unsat only going down by like a constant? Okay, that's um good. All right, so powering. Okay, so let's set aside the graphical aspect for a moment. If I kind of wanted to try to ramp up unsat, okay, so somehow if something makes a few mistakes, I want to make a problem where it has to make a lot of mistakes in some sense. What can I do? How can I sort of like amplify the error? So you want to add more constraints, but what kind of constraints? So I want to make sure that if the okay, so I want to take my original CSP. I have a bunch of constraints. Don't worry yet about the edges, because the first idea you'll do will kind of destroy the graphical part of it. So we'll have to figure out how to make the idea graphical. I just want to first amplify the error. So I want to take my CSP and kind of make it like harder. And the net effect should be if my original CSP was satisfiable, the new one will also be satisfiable. But if you can only get like uh, at best 5% error on the original one, then you should only be able to get 25% error on the new one. Yeah, but you can't just like copy and paste the constraints twice because they'll still stay 5%. But yeah, you want to somehow do something to ramp it up. You should be working with the same constraints, so to speak. Yeah, something. So yeah, okay. So I'm going to help you flesh this out. So what's one way to think of 5% error? Well, I pick one clause at random and check to see if it's right and see if it's 5% or not, right? And if I wanted to make an experiment like that, but get it up to 25%. Oh, so if instead of just choosing one constraint, sampling one constraint, I sample two constraints and check if both of them are correct, and if not, right? Now I'm kind of multiplying things together, right? Or if I do it 5 times, right? So there's some kind of like taking conjunction of constraints. So out of all the constraints, I look at all pairs of constraints and say, okay, now I have m squared constraints. I've checked this is right and this is right. Oh, a product graph. Yeah, okay, let me think about product graph. Okay, Well, we're not going to try product graph, but I haven't thought of that. Yeah, maybe that's worth thinking about. Okay. Okay. So, so this is the thought experiment. For every t constraints, I'll make a conjunction of t constraints. Oh, okay. Okay, I think okay. So unsat p is oh, that's okay. So uh, right. So it should be something related to unsat g, right? So what would actually the new unsat be relative to the old one? 1 minus unsat g to the t? Sounds right. Okay. This is roughly t unsat g, the first order term. Okay, think of unsat g as being very small because that's the regime in which, we're really trying to go up from 1 over m, right? And t is a constant. So, okay. And then, but now how many constraints do I have? There's nothing in the box. How many constraints do we have now? Yeah, like m to the t, and then like this. Okay. All right. Okay, maybe this will be our last question we address, and then we'll call it a day, which means we have one more slide. Okay. So this is a good idea because it's improving our unsat, but we lose the graphical part of it, which will be useful. It'll make more sense why it's useful later when we kind of do the full cycle. So how do we emulate this in a graph? Now, one suggestion was a product graph. Okay. But one concern is now every vertex is two different vertices, but I kind of want to make sure that like all things involving an original vertex V have the same label, which gets a little bit messy with the product graph. Because now a vertex V has like one copy for every other partner, and imagine G was a complete graph. Then how could you simulate this? I mean, yeah, not quite complete. Something like this. Or G's an expander, right? So random walks mix well, things like this. So think of G being an expander. So we're trying to simulate this experiment of picking T random constraints, right? And what's sort of the graphical version we've been doing recently? T length random walk. Pick a random vertex, walk around for T steps. Okay. So that suggests that maybe for every T edge walk in the graph, I make a big conjunction. So now you have some walk, and that's going to be a new edge from the endpoints. Okay. So that's what we're going to do. Is that we are going to sort of look at the power graph where I look at all walks of length 5 or something, which correspond to 5 constraints. Okay. So now this gets a little bit confusing because we have the only interesting part is how do I come up with at the end an alphabet and stuff like this, right? Because now I have like a 5-thing walk, right? And then the vertices are just the endpoints, which just have one letter, right? Which doesn't make sense because a constraint is supposed to kind of consider all the letters in between, on all the intermediate vertices, right? So what we're going to kind of have to do is each vertex is going to have now a ton of letters, one letter for every kind of vertex nearby, right? So each vertex has its own idea of its neighbor's letters. its own idea of its neighbor's letters. Does that make sense? So that when I look at this whole clause, I check to see if, oh, if, there's all these intermediate vertices that have disappeared because I've just added the endpoints, right? So to plug in those letters, I'm going to look at, oh, what does this vertex think that intermediate letter should have been? And what does this vertex think this intermediate letter should have been? Okay, so we want to, so like a four-step walk, and we're looking at the clause with over the whole conjunction, right? So that means there should really be four letters going in. But these two vertices only have two letters. So how are we want to define something like the conjunction of these four clauses. It's kind of expecting four letters as input. But the vertices themselves originally only had two. So I think we are going to reuse it. But so okay, let me explain what we'll do. So let's look at for each vertex, the neighborhood of everything. I guess within here 2 hops. Okay, maybe degree 3, so it's like 3 squared or something. Oh no, that's 3 hops. And we're going to take our alphabet. Let's say our alphabet was one of 10 letters. Okay, and we're doing degree 3 with 3 hops, so that's 27 neighbors. At most 27 neighbors, right? Now what we're going to do is we're going to label each vertex with 28 letters. Okay, the first letter will be sort of, we think of as the original letter for V. And then the remaining 27 letters will be like labeling the neighbors. Okay, so each vertex is going to sort of, at some level, be carrying labelings for the entire neighborhood, enough to swallow up these walks. Okay, so now that when we look at, some constraint that corresponds to a 3-step walk, okay, it goes to some U, right? So in our auxiliary graph, this will be a new constraint. Okay, and the idea is this constraint is only going to be satisfied if, when I look at the letters that V effectively assigns to these vertices, okay, those remaining 27 letters, they satisfy each of these individually. And same with U. U satisfies, it'll also have its own labeling of these edges, satisfies all of these simultaneously. And we'll add another constraint. We'll also encode in this constraint that U and V agrees on all these letters. Okay? So in order to just make this whole conjunction along walks make sense, we'll have to kind of blow up the alphabet size. Okay, which can be interpreted as each vertex having some idea of everyone else's label, and then forcing some consistency in the constraint. Okay? So that's where we'll end. So it'll be something like this. So for each walk, things will only be satisfied if V0's labeling satisfies the individual constraints. The other endpoints labeling satisfy the individual constraints. And on everything in between, they agree. That makes sense? So we'll analyze this next time. Okay, and I'll also remind us again, because this part's a little bit confusing. Okay, but that's what we'll do to try to amplify the unsat. Okay, thank you. All right, let's get started. So we're continuing probabilistically checkable proofs, right? So we've been talking about these expanders, de-randomizing things. We're going to build on those techniques. So just to remind us, we're trying to prove this PCP theorem, which is a probabilistic spin on MP and MP hardness, right? So NP means this is a problem where you can verify the affirmative in polynomial times. You want to know, is X good by some definition of good? That may be very hard to figure out, except there exists some certificate, Y, that would let me confidently decide it's in the language, right? Is there an independent set of size 100? You just give me an independent set of size 100, right? And then I can check and be convinced, okay, there is an independent set of size 100 in this graph. So, good. So, probabilistically checkable proofs, we're trying to figure out if there's some ways to have proof systems that can be like sampled, right? That can be like, I only have to look at a few bits of the proof and with some confidence be like, yep, probably correct or probably wrong, right? So this is like exactly what you're looking for when you're designing an exam you want to grade. You don't want to read everything. You just want to look at a few bits and be like, yep, that's right, or yep, that's wrong. And you should probably randomly sample so that for adversarial reasons, right? So so that's the idea. So the probabilistically checkable proofs is R random bits and Q queries. Usually it's log n random bits per query, but given X and an oracle access to Y, okay, so some proof, and we just assume oracle access because it's no fun to just read all of Y. So you're allowed to choose a few spots to query, and you do some random bits to get there, and then you query those parts of the proof. Oh, show me the 10th bit, the 100th bit, the 500th bit. I look at those 3 bits and I say, yeah or no. Okay, and so the rules are, if X is an L, then there must be some proof where you always accept X. And if X is not in the language, if X should be no, then for any proof, you should reject it half the time. Okay? So in other words, like to go back to that independent set thing, and say, oh, is there an independent set of size 100? And you say, oh yeah, here's an independent set of size 100 or something, right? But I'm not going to look at it. I'm just going to like look at 3 vertices and see if they're next to each other, and if not, I'll just answer yes, right? And that would certainly satisfy the first thing, which is either soundness or completeness. I don't know, right? Like if it's independent, they are independent, I won't find any incidences, so I'll be correct. The issue though is this 1/2 part. So if I just did that thing I described for independent set, there may be one mistake in there, right? There may be 2 vertices that are next to each other. But the odds of me picking that out by random sampling are very low. They're like 1 in n or something. So the question is, can you come up with a proof system that like has a lot more redundancy built in? So you're not trying to figure out the difference between like 0 mistakes and 1 in n mistakes. It should be 0 mistakes and 50% mistakes or something like this. Good. Uh, yeah. To query 1 bit of the proof. So I declare, give me the bit at location 101, and the oracle tells me, oh, it was a 1. Yeah. So I really want to say that I only have to look at a few bits of the proof to be able to come up with some idea of whether or not to accept it. Yeah, yeah. So the smaller the Q, the more impressive. Like if Q is polynomial in n, I could just read the whole polynomial size proof and then you just get back to NP, right? But to say that I only have to look at a constant number of bits, which is what the PCP theorem is saying, and be able to decide something with confidence, right? Probability 1/2. That's very impressive, right? And if I want to make the probability smaller, I can just repeat, right? So I can make the probability 1 in 2 to the 100 by using 100 times this, yeah. So that's what the PCP theorem says. It says that any problem in NP, okay, can actually, there's some proof system for it by which you only have to query a constant number of bits and be able to decide whether or not it's in the language with constant probability, one-sided error. Right? So that's an amazing statement about like robustness and things like that. And it leads to things like showing that getting better than 7/8 for 3-sat is NP hard. Okay. The opposite direction is sort of somewhat easy to see if you're trying to distinguish between 7/8 correct and none correct. If at least 1/8 of the set of the clauses are wrong, then you can actually sample a clause and have a decent chance of finding a mistake. Right? So this is the thing, it's hard to distinguish between like 7/8 correct and completely correct. And for that problem, you could actually have a PCP where you just sample a clause and you have a decent chance. You probably want to sample like 8 clauses or something, or log of 8 clauses. Okay. All right. So, and our setup was okay. So this one, if you might remember, it's not hard to see why PCP was constant queries log in random bits is a subset of NP. Because if you give me that kind of PCP system, um, I can try all of the possible bit strings. Okay. Oh no, I guess the proof, the NP proof will be the queries for all of the possible bit strings, the query answers. Good. Or no. Okay, sorry. If you had a proof that then PCP was constant number of bits, so there's some Y where you only have to look at a constant number of entries. That can just be your proof for the NP verifier. And what the algorithm will do is it'll try all random bits and just check. So just loop over all possible random bits. There's only polynomially many of them. Random bit strings, right? 2 to the log n. Okay, good. The harder direction is the opposite. Take any NP problem. And we're going to do something based on 3 coloring, but a little bit more general. These are constraint satisfaction problems with respect to graphs. So, well, okay. So a constraint satisfaction problem in general is you have a bunch of variables that can take one of something from an alphabet. In a simple case, it's true, false. It could be colors in a graph coloring problem, but in general, a finite alphabet. And you have a bunch of constraints. The constraints take a subset of the variables and say, oh, it's good or it's not. Okay. So it's a generalization of SAS, a generalization of coloring, all these things. And we're letting for a particular problem P, I'm letting unsat of P be the minimum error you can get, right? So in general, it's NP hard to figure out if it's 0 or not. Okay, but we're going to want to keep track of unsat because we're going to try to ramp it up. And this is what we're going to try to prove, that we can define that it's NP hard for the following problem. I give you a constraint satisfaction problem where every constraint has a constant number of variables. So there's many variables, but only a constant number participating in each constraint. And each variable can be one of a finite alphabet size. Okay, so constant alphabet size, constant number of constraints, of variables per constraint. And you're trying to decide if either all clauses can be satisfied simultaneously, or you can't do better than half the clauses. Okay. So that means if it's anything in the middle, you don't get punished. You can say whatever you want. You're just trying to distinguish between completely correct and half wrong. Right? There's a huge gap, and the claim is that it's still NP hard. And we went over last time that this theorem, that this half unsatisfiability for CSP is equivalent to the PCP theorem. Okay. Good. It has a little bit to do with the fact that, PCP, half of the bit string should not have a mistake. And so that 1/2 maps to half of the clauses. So each bit string ends up mapping to the clause. So we did this last time, so I'll go through it. Those who missed last time, it's going a little more slowly in the notes. Okay, so we are going to look at graph-induced CSPs, in part because we have built up these graph tools to ramp things up. And we're going to want to do some ramping up on the unsat. But, somehow doing it graphically lets us control the ramping up in certain subtle ways. So we have this graph toolkit, and we're going to use it. And so our starting CSP would just be 3 coloring. Okay, so here you just give a graph, and each edge is its own constraint. It just looks at the 2 colors, which are 2 letters, and sees if they're the same on the endpoints. Okay. So we know it's NP hard to decide if for a particular graph CSP problem, whether you can get zero error or 1 over m error if there's m edges, because 1 over m is the minimum, right? So you want to know if a graph is three colorable, that means you just want to know if there's zero mistakes, if it's possible to get zero mistakes or not. Okay? So what we want to do is we want to start with a simple problem like three coloring, and we want to take that 1 over m, distinguishing between 0 and 1 over m, and ramp it up to like 0 and a constant for some constant. Okay, so we're going to try to put this thing on steroids. And then once you get it to a constant, then you have something that's sort of in PCP land, right? If you want to test to see if something's happy, then you can just check a random edge, and with constant probability, if a constant number of them are mistakes, with constant probability, you'll find it, right? So once you get to a constant, you're basically okay. Okay. So what you want to do is you want to be able to take a problem where it's impossible to get them all right because there will be one mistake. And you want to somehow like layer or ramp up the error so that the mistake will kind of infect a lot of stuff, right? So what we're trying to avoid is hard to detect mistakes. And we want to somehow make this very redundant problem where now the complexity has moved to deciding between no mistakes or constant fraction mistakes. All right, so, oh no. Okay. Okay. So there's three transformations. I should make maybe one more comment is that, this is sort of the last topic, and it's a little bit up there, right? It's a little complicated, and I won't be able to do all the details. It's not clear that if I did all the details, you would even absorb all the details because there's just a lot. So I'll do a lot of the details, but it's semi-impressionistic. Okay, but I think there's a lot of also styles of thinking involved in this topic that maybe you haven't seen as much before. Trying to ramp up the error, and you also see a lot of connections, right? Because P versus NP is a question you already knew about coming into the class, and somehow we're making connections, and somehow randomness is giving a comment about exact solvability, hardness of approximation, right? Just knowing that these ideas are in the same space is unbelievable, right? Just the fact that without a handle on randomization, I couldn't make certain comments about 3-SAT being hard to approximate is just already a big theme, right? So, I don't know if we need to understand all the details perfectly to walk away being like, okay, there's some connections here. This is kind of interesting. Yeah. But we'll still be able to do most and be able to reinforce some of the skills that we've developed over the past couple weeks. Okay, so there's 3 steps. The first one we've already covered, and the second one we started. So there's going to be 3 steps that kind of go in a cycle, similar to someone like the zigzag product and stuff we did before. Okay, and so one step is to make the graph into a constant degree expander, which it's hard to completely motivate at this stage of abstraction, but you've seen that useful before, right? Somehow, like constant degree expanders, they have very good properties. They're sort of well connected, so things mix well and things like this. Random walks are really well behaved, but if they have constant degree, they're also very sparse. So of course, you could add all the edges and you get a well connected graph, but then things blow up in size. You don't want things to blow up in size that much. So we want to make things kind of nice. Powering is where we're really going to try to ramp up the error, and that's where we left off last time. So I'll try to get us there quickly. And then when we do powering, now it is going to correspond to a graph power, what we're doing to the underlying graph, but it's going to do weird things to the constraint satisfaction problem, right? So in the graph CSP, we have edges, and each edge corresponds to some Boolean problem, right? It only accepts certain letters. And so now you're going to start having like a formula corresponding to a path or a walk in the original graph when you start powering things up. Okay, so now things are getting kind of mixed up, and naturally the alphabet's going to kind of blow up. Okay. So in addition to degrees getting bigger, just from graph powering, the alphabet's going to get bigger, and we want the alphabet to stay constant. So there's a third step called alphabet reduction where you try to bring the alphabet down and you lose some other stuff. Okay, so there's going to be these trade-offs where some things are getting out of control, like the degree sometimes goes up, then it goes back down. Number of vertices changes a little bit. The unsat value hopefully is going up over time. We want to be able to do kind of a full loop and get the unsat value higher while keeping other things constant. The alphabet size will blow up, we'll bring it back down, things like this. So hopefully when all three things are combined, the trade-off will be worth it. You'll end up with another graph CSP with kind of same degree, same number of vertices roughly, same alphabet size, but the unsat value has gone up in one round trip. It's involved. So the funny thing maybe about this is that last time we used to work really hard to make things into a constant degree expander. Like the zigzag product was like, so involved to bring the degree down. But we actually don't do any of that. Okay, we actually do something much simpler. So we have two steps. We want to make it constant degree, and we want to make it good expansion, make it an expander. So to make it constant degree, you take each vertex, okay, and you're gonna like split it up, one for every edge. You have a copy for every edge. And normally you might just add like a cycle to connect them, like if you're doing connectivity. But here you want to actually, and you can add like you have to make a constraint for each one, right? So with all these auxiliary vertices, you can add an equality constraint, saying, okay, this vertex needs to have the same letter as this one, this one, this one, this one, this one. Okay. Now it happens though that so you add a few, if you just did a cycle, then you add a very sparse, equality constraints, right? Which if you're doing exactly, you would have to make them all equal. But we are in like an approximation regime where, there's an unsat value. And so there could still be it could still be favorable for the bad guys to screw up some of them, make some one letter, make some another letter in order to satisfy those edges. So instead of a cycle, we want to do something better connected. So you end up putting an expander in between. Yeah. Even if it wasn't, you can do this on the first step. So we're going to blow up each vertex and add an expander inside, which is not that many edges compared to a cycle. It's only a constant factor more, but things will be better connected. Okay? So that, you should just think of it as a proxy for a click, which is super connected. And so if you do this, your number of edges are going to increase by a constant factor because you're adding a sparse graph. And your graph will be a regular graph if you added a regular expander. Everyone has the same degree. Okay. And, your unsat value is going to go down a little bit, right? Because, our goal is to eventually get the unsat up and up, right? But when you blow this up, now, you're allowed to actually give different letters to the auxiliary copies and stuff. You lose a little bit because of the expander equality constraints. Okay. So, but you do have a few more degrees of freedom. So it gets a little, unsat goes down a little bit, but it's only going to go down by a constant. And this constant will require the fact that the expander is, well connected. Okay. So it's laid out as an exercise, in the notes. If I had done this lecture, 2 weeks ago, then it would have been on the homework. Yeah. No, you have or maybe one vertex per edge coming in. So in total number of vertices will be like m over 2 or something because you're double counting. M is the original number of edges. Okay, well, in the very, very first step, let's just say you start with your graph coloring problem. Maybe it's not regular. Okay, and you want to know if it's perfectly colorable or not. You make that into a CSP. You want to know if it's satisfiable or not. The first step will just do the thing with a cycle. And then, because the first step, you just have to do 0 or not 0. So the cycle's okay. The cycle is just not strong enough for the quantitative version, where we're trying to, cycle would make unsat G prime go down by too much because there may be a huge advantage to giving different letters to the thing. So if you add more connections, then you can show it's bounded by a constant below. It's not too bad. That's why it was left as an exercise. I think I gave a hint though. Okay. All right. And then, so that would address the degree, and the part where you make it an expander um, is kind of funny. You have n vertices and it's not really well connected, so I'm going to make an expander with n vertices and just throw it on top. Okay, and just add a lot of connectivity to the graph. I'm not adding too many edges. Okay, and the constraints for these edges will be like the trivial one. Any letter is fine. You automatically satisfy this constraint. So this is just making the graph spectral properties good, but adding a bunch of like freebie edges, right? So maybe you had like a million edges in your graph and a million constraints, right? And now we're going to add 5 million more edges to make the graph connected, and just say those are free points, okay? So the unstat's going to go down by 1/6 or something if you're going from 1 million to 6 million total. Okay, so it'll go down by a constant factor. Okay. But that's okay. So in general, decreasing unsat by a constant factor is kind of okay because we're going to increase unsat by like a large factor. Yeah, later. What's upcoming? Okay, good. So that's step one. So you make the graph CSP, the underlying graph, a constant degree expander, and unsat G is going to go down by a constant factor. Okay. We are. You're going to push it down. So step two is going to let us increase unsat G a lot. So there's going to be some trade-offs. Yeah. So now step one is really kind of cleaning. All you really care about is step two to increase unsat G, but it makes a mess, and the other steps are cleaning it up. Okay. So good. All right. So we did this last time. If you wanted to take a constraint satisfaction problem and you want to increase the unsat probability, the error probability of error, right? So one way to think of the unsat is, suppose I pick a random constraint. For an optimal solution, what are the odds it's not satisfied, right? And that will exactly give you unsat of that problem. The probability it's not satisfied. So if you want to ramp this up, you say, okay, let me sample 5 constraints randomly and check to see if all of them are satisfied, right? So it's only correct if all 5 of them are correct. So your unsat is going to go to like 1 minus unsat G to the T. Okay. Yeah. Which is roughly T times unsat G when unsat G is small. And unsat G is really small in the case we're interested, because once unsat G is at least a constant, we're done. Right? So as long as unsat G is small, this is basically T times unsat G. So basically, if you can just do bundles of T of them, you'll increase by a factor of T. And your number of constraints will go up. Now the only issue with this is that if you started with a graph and I just willy-nilly pick T at a time, you will not end up with a graph. You'll lose this graphical property. Okay? So to this end, what we want to do is we want to do sort of like a graph power. Okay? So now, instead of like sampling, so now G is an expander, so random walks almost look like totally random sampling. So instead of randomly sampling 5 constraints and kind of combining them, I'm going to pick a random vertex and take 5 random steps, right? And that'll give me 5 constraints, and I'll just combine those 5, right? And I'll do that everywhere. Okay. So, we pick some T and we look at all the T step walks and we combine them. Okay. Good. Now, one thing that happens, let's say for simplicity, there's like 3-step walks or something, right? So you have a walk of length 3, and you want to make a constraint that's sort of combining them, right? And that constraint is saying, okay, are these 2 letters okay for this edge, and these 2 letters okay for that edge, and are these 2 letters okay for that edge, right? So there's like 4 letters involved, but you're looking at a constraint only on the endpoints, right? Which used to only have 1 letter each. So you're short the 2 middle letters. Okay. So the way we're going to address this is, so if T, okay. So if the graph is like regular was degree 5 and t is 3, it's only going to have like 5 times 5 times 5 neighbors that are 3 hops away, right? So that's 125. So what we're going to do is we're going to have each vertex, instead of holding just one letter, it's going to hold on to 126 letters, okay? Which I interpret as one letter for me and one letter for everyone in my neighborhood. You know, some fixed ordering of the things in the neighborhood. Yeah. Well, yes and no. So it's similar intuitively, but maybe the way the numbers work out when you calculate unsat G, you know, you want to be more precise. Okay. But the first sort of thing is just to get like a graph CSP. So for a graph CSP, each vertex needs to have a letter in some alphabet. Okay. So that I can just plug it into the clauses. So yeah. So there'll be two different constraints. Well, so satisfy both. So so for every possible walk up to of so many hops, which include like going there and back and you know redundant things, that'll be a constraint. Okay. But the real issue is that I want to have some alphabet where I can look at just the two endpoints and see if the constraint, which is really many constraints along the middle, is satisfied. Okay. So what's going to happen is every vertex is the alphabet in the new powered version is going to look like a bunch of letters. Okay, so I'm going to take my 10 letter alphabet and turn it into 10 to the 126 letters, which is really 126 uh, choices of one out of the 10. Okay, so A is going to go to A to the D, where D is the maximum number of vertices in a neighborhood. Okay, and what we're going to do is, so a vertex is assigned A to the, you know, D letters, basically, which we interpret as, you know, for each vertex in a neighborhood, it's sort of like V assigns letters to other vertices in its neighborhood. Okay. So, sorry. How, by having edges? So, 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 so in this example, the degree is 3. Okay. Every vertex has, or maybe degree is actually 4. So this picture is not perfect actually. So the degree is 4, although this guy is missing an edge, and it's 3 hop, 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 right? So there's like, you know, 3 cubed or something vertices. I guess it's actually 4 times 3 times 3. But yeah, I mean, if yeah, if it's degree 4, there should be a fourth one here, but then everything else has 3 branching out. Yeah. Okay. So there's some neighborhood, and we're going to basically, you know, in the new problem, the alphabet will be way bigger, but it's going to be interpreted as for a particular vertex, it's assigning a letter to each neighborhood, including itself. Each vertex in a neighborhood. Okay. And then our constraints. Oh my gosh. We might not catch up to where we left off last time. Okay. Our constraints are like this. So if I have a walk, you know, from V0, V1 through VT, right, with all these edges in between. Okay. Now, I want to make a constraint in this powered graph. So the endpoints are just V0 and VT, which have a bunch of letters that are assignments to the others, right? So what we're going to do is this. I'm going to first look at V0. So V0 is going to have letters for each of these. And I'm going to say, are V0's assignments, do they satisfy E1 for V0 and V1? Do they satisfy E2 for V1 and V2? So does V0's, you know, proxy assignment for the other vertices satisfy all the constraints? Okay. And we'll do that also on the VT side, right? It's an undirected graph originally, so they'll have labels in the opposite direction. So VT will have labels for all the other vertices along this walk and say, okay, do VT's labels, its proxy assignment, do they satisfy all the clauses along the way? Okay. And then finally, there's one way to cheat. Maybe V0 has some good letters for V1 to VT, and VT has good letters assigned to V0 to VT minus 1, but they have different letters, right? We're not allowed to do that. So our third constraint is V0 and VT should agree on all of these vertices. They have the same letter. Okay? So that would be the whole constraint for this walk. All right. So this is why the alphabet blows up. Okay. Good. Yeah, that's okay. I think you guys get the idea. So this picture is not very useful. Okay. Um, good. Let me put it this way. All right. Okay. So here's a proof. I don't know how much we'll get into it. This really like makes this 50-minute format absurd. Okay. So the claim is that our unset, we're trying to make it bigger. It'll go up by at least square root of t compared to before. At least when unsat g is small. Okay, so when unsat g is big enough, then you don't care. So as long as unsat g is small, t is some constant, it'll go up by at least the square root t factor. Okay. So if t is sufficiently large, then, for example, you'll go up by a factor of 2. Okay. Good. All right. So how do we prove this? Or like, what's the starting point? I just want to get like the setup going because it's a weird statement to parse, right? So I figured if we can come up with a setup, then at least it means we're understanding the statement a bit. Okay, so you can start with an optimal solution for the problem in g to the t, right? That's with the huge alphabet and stuff. So it has, unsat g to the t of them. And we want to take that and we want to show that, if we want to show that unsat g is smaller than this value divided by square root t or something, then we need to take the assignment in the lifted one, in the powered one, and get some assignment in the original problem with small error. Okay, so we're trying to show that, okay, if you have this medium error in the powered version, you should get smaller error in the original version. You shouldn't be able to get, yeah. Okay, good. So that's what we're going to do. We're going to start with some optimum assignment in the powered problem and try to figure out some assignment in the original problem that has good error relative to the original one. I mean the powered one. Okay. Okay. So any ideas for how to come, yeah, because any idea is fine. So I give you some labeling in the powered problem. How can I come up with a reasonable label in the original one? Yeah. That would be a great case. So if pi bar always kind of, so two different vertices have a different opinion of this vertex in between them, right? But if we knew that everybody always agreed, then we can just use that common one, right? Now, in general, that might not be the case that they're agreeing because unsat is just doing the best it can do to minimize the thing, and that doesn't necessarily mean they always agree. Maybe strategic not to agree. So we want to do something like that that would agree with that if it were so nice, but somehow is a little more robust. So here's what we'll do. Okay, so we start with this optimal labeling in the lifted space, and now we want to choose a label for a vertex v. Okay. So in general, all these vertices around it have opinions of V, right? You don't really know which one to choose, but you could like take a popular vote, right? So you could like take a random walk from V and wherever you land, take that label, okay? Or you can take, what's the most likely label from this experiment. Okay, so what we'll actually do is we imagine taking a T over 2 step random walk, lazy random walk, I guess, from V, okay? And we'll define pi V, to be the most likely letter you find, right? So in general, vertices around you have opinions about you, and they'll tend to try to agree because otherwise they'll have to forfeit a lot of constraints. And so we kind of want to do something like a majority vote. So what we'll do is we'll figure out the most likely letter to come up from a random walk of T over 2 steps. Okay? So that's sort of some kind of general consensus around you. So one thing to note is that at the very least, the probability that the random walk will get the letter that you assign, okay? So the probability that if I did this random walk, the label I assigned is equal to where I end up, is at least 1 over the size of the alphabet because it's the best among all the letters. Probably any letter with 1 over size of A is all you need, and that's at least a constant, okay? Because our alphabet is held constant from the following step. Okay. Good. Good. All right, so some high level ideas in case I hadn't been high level to this point. So what's the intuition? Okay, so let's say that our induced labels fail some constraint CE. So to be clear, our labels are deterministic, right? It's based on a random experiment, but it's ultimately just extracting the most likely thing, which you can just calculate explicitly. Okay, so it's fixed. So now suppose it fails a particular constraint, right, with endpoints U and V. Okay, now my label for U, my label for V is based on like a majority vote from random walks from U and random walks from V, right? So that means that, if I take a random walk from U and V, right, and how would you put this? Okay, so these two endpoints, right? This will be some constraint in in the in the in the powered problem, right? Because it corresponds to a t-step walk. Okay, so if you are failing this edge CE, then if you took a random walk from U and V, then there's going to be some constraint in the lifted problem that you're probably failing, right? Because the endpoints tend to give you bad. And that powered edge, the walk constraint requires everything to be happy, right? So that's sort of the idea. Yeah. So this fails a constant probability. So one way to think of it is saying that, okay, if you're failing this constraint CE, then, a constant fraction of those edges in the powered problem that have E in the middle are failing. Now, this is certainly true if E was exactly in the middle, because then you do T over 2 on each side. Okay? But now, what if we want actually a little bit more? So it should also be, we want to sort of relax in the middle to allow for also like T over 2 plus 1, T over 2 plus 3, so that we can fail more constraints. Right? I want to fail all the constraints with this bad edge in the middle, and all of these constraints with bad edge off by 1 in the middle from the middle, and all the constraints for walks is the edge off by 2 from the middle, maybe up to like square root T or something. Because I want to say that if you're failing this edge in G, then you're failing a lot of edges in GT. So this is why we have to do lazy walks. Um, anything down here? No. Okay. Right. Okay. So this, okay. Yeah. All right. Okay. So we need two lemmas, I guess. Um, right. I think I was supposed to erase some of this, but that's okay. All right. So let's start with the first line. Okay. So this is looking at all the indices that are really close to t over 2 within square root t. Okay. The reason square root t is because that's one standard deviation of flipping coins, t coins. Okay. So so we want to claim that for all these indices very close to the middle, okay, uh, with constant probability, uh, the vertex endpoint, the label for v is the same as the label for a walk. That's I steps away, where I is almost t over 2. Okay, so because v was originally assigned as I'm starting at v and I take exactly t over 2 random steps, and then what's the most likely label on the other side. Okay, but here we're saying that for any I that's very close to t over 2, the square root t away is considered small when t is large. Okay, if I had gone to v and I had gone I steps, not exactly t over 2, almost t over 2, and then looked at what that vertex thought of me, I'll get a very similar distribution. Okay, and the idea is that, well, when I was deciding how to define the label of v, we actually did, I don't know if I made this clear, we did t over 2 lazy steps. Okay, so each step I might actually take a step. Okay, and if you just look at the binomial distribution of like, okay, you're flipping coins, t over 2 coins, or if you're flipping t over 2 plus square root t over 2 coins. Okay, so square root t it's actually close. I mean, when t is bigger, the blue and the red will look more and more similar. Okay, so all you really care about is how many real steps you took, and then the label on the other end of the real steps, right? And if I'm looking at 100 or 101 lazy steps, the number of real steps is going to be really similar. If I'm looking at t or t plus square root t lazy steps, the number of real steps is going to just be distributed really similarly. Okay, so as a result, for all I and I, you're going to get a very similar probabilities for the opposite endpoint. Okay, so what the lazy random walk does is it lets you blend together t over 2, t over 2 plus 1, t over 2 plus 2, so forth. Okay, so the picture is just this. The distribution of the real steps you take is going to be so similar, the distribution of labels will be almost the same. This again, I think, is left as an exercise. Okay. But this is just plugging in the binomial theorem. Okay. Okay, I'm going to sneak in 2 minutes. All right. So the second of two lemmas that you'll need, okay, is the following. So think of the original graph, the graph CSP, as having good edges and bad edges. The bad ones are the ones that are failing, which you'll label, and the good ones are everything else. So mu will be like and remember, the constraints are coming from random walks, right? And if the random walk has a single bad edge, the whole constraint fails. Okay? So we're interested in questions like, if I pick a random walk, vertex, and I walk around for a little while, like t random lazy steps or something, what are the odds that all the edges are good? Or what are the odds that I get at least one edge, right? Which is almost exactly like what we did last time in terms of what are the odds I get stuck in the bad vertices, except this time it's what are the odds I get stuck in the good edges. Okay? So you'll get, and I think we'll do this together at some point, maybe next year, you'll get something that looks very similar to what we had before. This 1 minus gamma to the I term. And this is where it's important that G is an expander. Okay? So I'll try to end it there. I just want to see what comes next. Okay, so I think our next step then is going to be to try to combine these two lemmas and try to show this inequality highlighted in yellow at the top. Okay, taking that tth power is going to increase unsat t by square root t, but you already see some of the ideas starting to come together, right? So we've now extracted from the powered solution a solution, our own graph, and these ideas of like, okay, a walk is bad only if one of those edges is bad. One of the edges are bad, and we have to tie all that together, and that'll get the amplification. That's kind of some high level idea. So we'll see what happens next time. Okay. All right. Thank you. We made a little bit of progress today. I think we got through like 4 more slides. Yeah. Okay. All right. So we got to try to finish this today because we're running out of time. So we did this starting on Friday. We did it Monday too, but we spent most of Monday going over what we did on Friday. We only advanced like 5%. So I'm going to try to go a little bit quicker. So we're trying to do probabilistically checkable proofs. Again, the PCP theorem itself says that whereas normally in MP problems, you read the entire proof in polynomial time, PCP says that any problem in MP you can come up with some kind of proof structure where you only have to check a constant number of bits to be correct with constant probability. Okay, so that's remarkable. It leads to approximation results. But we had reduced it to looking at constraint satisfaction problems. So SAT would be an example, graph coloring would be another. But you basically have a bunch, yeah. It's log n bits. Oh, you need log n random bits, and you're going to sample a constant number of bits from the proof. So you probably weren't here Friday or Monday, but yeah, so we can set up proofs so that I can just flip a few coins and check only a small amount of the proof. And with some confidence say, oh, it's either incorrect or not. So that would be like me grading your homework and just like instantly or only looking at a few bits instead of reading your solutions in detail and figuring out if you're right or wrong. Yeah. So we had, hopefully, I'm a little behind on uploading videos, but we had longer discussions about this. And I want to make sure that we leave Friday just to, answer any, just hang out and hang loose. So in a constraint satisfaction problem like SAT, you have a bunch of clauses and you have variables. And as opposed to, like, it's going to be a little bit more general than true or false. And then there's an alphabet. Each variable is given a letter from an alphabet. And that constraint looks at, I guess in a Q-ary one, we'll look at Q different variables and, certain particular letter assignments satisfy and others don't. So just kind of a little more general. So another example would be graph coloring. So each edge is a constraint and each color is a letter. And the vertices are variables. So you assign the variables, the vertices, colors, which is like the variables, letters. And for each edge, you want to make sure that you don't have the same color on both endpoints. Okay? It's just that when we do the reduction, we actually start with graph coloring, but it gets messier and more general. So we want this more general thing. So what we're trying to show is that given this kind of Q-ary constraint satisfaction problem, so each clause has a finite number of variables, each of which takes a finite number of letters. So it's NP hard to distinguish between either A, you can satisfy every clause simultaneously, so you can figure out how to color the graph or something, okay? Or B, figure out if you can assign the variables so that at most half of the clauses can be satisfied. Okay, so in other words, we're used to just saying, can you completely solve it exactly or not? This says it's NP hard to figure out if you can even do half of them. Okay. So if you have something like this, then you can come up with a PCP for this because the proof would be the letter assignment, and I would just randomly sample a clause. And since you're either at least half wrong or completely right, if you're wrong, you're at least half wrong, and I'll find a bad clause. So So that's what we're trying to prove. This is equivalent to PCP theorem. We've already kind of discussed this, so I'll gloss over it. So the simplest one in the starting problem is just graph coloring, where each CSP is an edge, a constraint is an edge. And so we already know that because graph coloring is NP hard, so I'm letting unsat to be the minimum error, relatively speaking, 1% error, 2% error, things like this. What's the minimum error you can get? We already know it's NP hard to distinguish between 1 over M error, just getting one edge wrong, or 0. Okay, so normally that's basically exactness, right? Because 1 over M is the minimum. And we want to take that and we want to put it on steroids and increase 1 over M to a constant. Okay. So you might start with graph coloring, but it kind of immediately becomes general. And we do something kind of like a couple of our previous topics, where we're going to start with this kind of graph constraint satisfaction problem overlaid on a graph. And we're going to try to ramp things up. One is sort of a cleanup step, where we want to make sure the graph is a constant degree expander. The second is the amplification step. So here we really want to, because we want to start with 1 over M error and make it big. So the amplification step is where we try to make the error much bigger. And then as a consequence, the alphabet's going to get really big and you have to reduce the size of the alphabet. So compared to before, we were just playing with graphs and shaping the graph to our liking. Here we're shaping the graph, but simultaneously we have to maintain the constraints on every edge. And that leads to blowing up the letters and you have to bring that back down. So the first step we did, twice in a row probably. It's not too complicated. We take each vertex, split it up, replace it with an expander. Okay. That makes everything constant degree. And then to make the graph an expander, you just throw an expander on top of it. Okay, so you first just split up the vertices to make all the degrees small. But the expansion is not good, so you just overlay another expander with the same number of vertices on top. And the constraints would just be like a trivial constraint. Any letter is okay for this edge. Good. Now, the interesting one is powering. So this is the graphs, the thought experiment to motivate us. So if we don't worry about graphs for the moment, you have a constraint satisfaction problem, right? You have a bunch of constraints. And, unsat is like 5%. So that's like saying if I sample one constraint at random and check it, the error is 5%, right? 5% chance of getting it wrong. So if I want to ramp that up, then you can say like, okay, let me sample 2 constraints randomly and check if they're both right. Right? And that'll increase the odds of finding a mistake because now they both have to be right. And it doesn't have to be 2, it can be 3, it can be 4, it can be 5, it can be bigger, and that's going to increase the error a lot. Okay? The only issue is that this will destroy the graph part. We want all the constraints to correspond to edges. So given that G is a random graph, I mean not a random, it's an expander graph, you're hoping that random walks look like completely random sampling. Okay. So what we do is for each vertex, we take a random walk. Okay. Actually, we do a lazy random walk. And for each lazy random walk, we make a constraint that's sort of gluing all the constraints along the walk. Okay. Taking the conjunction. Now, what's going on though is, let's say there's 3 constraints from point A to point B, right? And you want to say, oh, you can only you have to satisfy all of them simultaneously. So you have 3 constraints and it's really got, 4 vertices total involved. 1, 2, 3, 4. And in graph constraint problems, you only have letters at the 2 endpoints. So when I'm replacing a walk with an edge, there's some mismatch there. So to deal with this, and this is where the alphabet blows up. So instead of just originally assigned 1 letter to each vertex. But now what we're going to do is I'm going to take V and let's say that I'm T is 3 or something. I'm looking at 3 hop walks. So V is going to look at all the vertices within 3 hops. Okay, it's constant degree, so it'll be like D to the T or something. Okay. And it's going to have, in my new problem, I'm going to assign it enough letters so that I can interpret it as like 1 letter for each vertex in the neighborhood. Okay, so assigning 1 letter, it's going to assign, 3 to the 3 or something, total letters to V. But I'm going to interpret that as, okay, V has a letter for this vertex, a letter for that vertex, a letter for that vertex, and so forth. So each vertex sort of has a local neighbor labeling. Okay, so that increases the alphabet size. And now for your new constraint, what you're going to do is this. Okay, so let's say you have some walk here, right? Which has, the edges in between represent these constraints, each of which is expecting one letter from each endpoint. Okay, and you want to take something like the conjunction. Okay, so of course, we're gonna replace this walk with one edge in a powered graph. Okay, and the constraint's going to be like this. Okay, so I have all these constraints I want to satisfy. Now V0 in the lifted bigger problem, right? It has this huge number of letters assigned to it, which means that V0 has an assigns some letter to V1, it assigns some letter to V2, it assigns one letter to each of the vertices along the walk. So I'm going to check, okay, is E1 satisfied by the letters that V0 assigned to these two? Is E2 assigned by the letters assigned by V0 to these two, and so forth. Okay? So we'll take V0's labeling of the other vertices and check all the constraints on the way. We'll do the same thing from the VT side. So the actual graph is undirected. So VT is going to have labels, and the bigger problem is going to have A to the D letters, which is going to include one letter for each vertex along the walk. And we're going to check, okay, do VT's labels satisfy this constraint, that constraint, that constraint, that constraint, that constraint? Okay, so by having each vertex or label the whole neighborhood, now I can do something for these kind of walk conjunctions. Okay, and so that's two requirements in our problem. And the third one is, maybe V0's labels do satisfy everything and VT's labels do satisfy everything, but they're using different letters. So that we want that to be cheating. So the third constraint is that V0 and VT should agree on everything in their overlap. Okay, so that's how we sort of do this conjunction bundling power trick, but to make it fit this graph CSP format. Okay, so you get a graph CSP where you are basically taking a conjunction of a lot of stuff. And if it's an expander graph, then these walks are looking like uniformly random samples. Okay, there's some degradation based on the spectral gap, but it's similar. But the problem is your alphabet blew up. Okay, good. We're making some progress. Going faster than last time, so that's good. Okay, I think when we got to this point last time, it was like 10 minutes left. Yeah. So for every path, you generate a new constraint. So the underlying, the new, so you're going to start with G. And, okay, so let's say that G has degree 5. And I said we're going to make a constraint for every lazy walk. So the first thing you do is you add 5 self loops to every vertex. And then you look at the powered graph. So the 5 self loops will bake in the lazy part. Okay. So then you look at the powered graph. So you look at all possible walks of step 5, including, using the self loops. So that could be, 4 or 3 or 2 steps in the original graph. Every single walk, you're going to generate a constraint in this fashion. So you're going to have same number of vertices, but way more constraints because every, combination of 5-step walk, including the self loops, is going to be a constraint. All right, good. So that increases the degree, but remember in the first step, we know how to bring the degree down, and it's not the end of the world. So degree we'll handle it later. Okay, so here's the real claim. So you're hoping, so T is a number of steps, and you're trying to make unstack go up, right? Because you're trying to start with 1 over m and get it up to a constant. So the claim is that if I look at this kind of powered problem, which I'm calling G to the T, okay, the unstack goes up by roughly a square root T factor. Okay, so you make T big enough, you should double your error. Okay, unless unsat G is already big enough that you're done. Okay. All right, so good. So how do you prove this? So what we started last time is, so to prove this claim, what we need to do is start with some labeling in the power problem, okay, that achieves unsat of GT. And we want to turn that into a labeling of the original problem. So this means it's assigning tons of letters to every vertex. And here's just one letter for every vertex. And then I want to show that the error in the original is much smaller than the error in the amplified graph. Right? So in the amplified problem, every constraint looks like a bundle of original constraints. And it's saying, okay, that problem should be much harder. If you're able to get 10% error when I'm taking all these conjunctions, then you should have gotten you should be able to get 1% error in the easier one when everything's still separated. That's what it's trying to say. Okay. So, by the way, same disclaimer as last time. I guess it's more an issue now for lack of time. But, this is obviously the most complex thing of the semester. And so we won't be able to do like all the details completely. But I still want to leave you with this impression of, okay, there's some connection between things like P versus NP, hardness of approximation, and randomization, right? Even that conceptual connection and seeing some of the tools come into play that we've worked on for the past couple weeks is already amazing, right? So I think there's some kind of deeper philosophical statement this is making that maybe we don't completely understand, which is one reason why we need such a heavy construction to get through it. Right, but clearly there's some interesting parts at play, which on the surface level, it's not clear there should be any connection at all, right? So, yeah. Okay, good. Okay, so again, we're still catching up to last time. So, giving a labeling for the powered problem, which is giving a lot of letters for every vertex, I want to come up with a good assignment of one letter per vertex. Okay, that sort of decreases the error. So what we do is the following. So for each vertex, so I'm a vertex V and I want to find a letter. Okay, so what we're going to do is we're going to take a T over 2 step random walk, lazy random walk. Okay, and then on the other end, you're going to find some other vertex that has an opinion of you, right? That other vertex in pi bar, the powered problem, has a label for you. Okay. Now you can imagine doing this experiment ad infinitum, right? And there will be some most common letter that appears when you run this experiment. Take 5 lazy steps, see what letter that vertex assigns you, right? And so different vertices may have different opinions of you, but there will be some most common opinion based on what you find in this random walk. Okay? I think this is called the mode, right? It's like the only time the mode has ever been useful. Okay, so the most common letter. All right, so that's how we are going to come up with letters for yourself. It's sort of like a majority opinion of what everyone else thought of you. Okay. All right. One basic thing to point out is because you're taking the mode, you should be at least 1 over the size of the alphabet. If there's 10 letters in the alphabet, whatever letter you picked should be something that happens at least 10% of the time. Okay, so it's at least a constant. All right. Okay, so what's the intuition? Okay, so given your assignment of letters, which is this majority opinion, right, based on T over 2 step random walks. Now let's say that I have 2 variables U and V, where that induced letter fails the constraint in between them. Okay, so majority vote letter, but it fails the constraint. Okay, so what does that mean? Based on how these letters got, that means that if I took a random walk for T over 2 lazy steps in this direction, and I looked at what letter it gave me, and if I took a T over 2 step lazy random walk in the other direction and saw what letter it gave me, with constant probability, those 2 letters are going to fail this edge. Okay, but then what does that mean? In the powered graph, these 2 endpoints are some constraint from this walk that goes through this edge, right? So that means if these induced letters are bad, which are based on majority votes, right? Then it's going to kill a lot of these conjunctions for random walks where it appears in the middle, right? Because this edge is sort of in the middle of a t-step lazy random walk because it's t over 2 from each side, right? So if this edge is bad and it's some majority vote of the neighborhood, then there's a huge number of constraints going through this edge that you're killing off in the original problem. Okay, so that's the idea. Okay, so to get the full result you want, you need, okay, so that's the idea. And so we want to show that the right. Okay, so there's two lemmas you need. Again, we're still playing catch up. So one is that, okay, so here I talked about an edge being t over 2 steps exactly away, right? But now suppose I move 1 step to the left. So, and I go t over 2 minus 1 steps this way, and I go t over 2 plus 1 steps that way. Okay, but they're lazy steps. Okay? In print, you would think the distribution is not very different, especially because they're lazy steps, right? So you can do a lazy random walk in 2 different ways. One way is each time you decide whether or not you're going to take a step, right? You flip a coin. Or, if you're going to take 100 lazy steps, let me first flip 100 coins and see how many real steps I'll take, 45 or something, and then take 45 real steps. Okay? So now think about t over 2 minus 1 versus t over 2 plus 1. Okay? And do the second version where you find out how many real steps you take first. That distribution is going to be really similar, right? There's not a big difference between flipping 100 and 101 coins and seeing how many come up heads. Okay? In fact, if you work through the binomial theorem, you can go up to like square root t, and things won't be that different. So flipping 100 coins, flipping t coins or flipping t plus square root t coins and see how many come up heads, that distribution is going to be very similar. Square root t for large t is considered small. It's 1 standard deviation, right? So you're often going to be close. So you're going to get this distribution that looks a lot like this. Okay? So as a result, so if you know that your letters are bad, so it's going to kill off a lot of the things that are t over 2 and t over 2 on each side. It's also going to kill off a lot of the things that are t over 2 plus square root t in this direction, and then t over 2 minus square root t in this direction. Okay? Things will go down only by a constant. Okay? To do this full proof fully, you would have to, write down the binomial distribution, double check. But what you do is you just do a conditional on the number of real steps you take and say, oh, that distribution is not that different either way. So you're going to get something very similar. Okay, good. All right. Now here is the next lemma. Okay, so okay, good. So okay, so let's say that in your graph, F is the set of, so this is where the expander part's going to come in. So in principle, these random walks should look like uniformly random samples, but there is some, difference. Okay, but this is just measuring the difference. So we've done something similar before where we said, okay, suppose there's a bad region of vertices I want to not get stuck in or something. Okay, if I randomly sample a vertex and I walk around, I have some decent chance of escaping. That came up in, I think, the pseudo-randomization lecture last week. This is something similar, but for edges. Suppose you have some edges that you're trying to escape from. Maybe these are all the edges that are satisfied, right? And supposedly there's a limited number. So the odds that your walk will always stay completely in this will be mu plus 1 minus gamma to the I, where gamma is the spectral gap. Okay? So this is, I think, almost the exact same as we had before. It's very similar form. So as you take more steps, you have a bigger and bigger chance of leaving. Okay, so what does this exactly say? Uh, yeah, okay, so if you start in F, then what are the odds that you stay in F? Will be like mu plus 1 minus gamma to the I. Okay. All right, so are we going to prove that? Okay, we're going to see what are the implications of this. Okay. So um, we're going to let F be the set of edges that are failed by our induced labeling in G. Okay. So mu will be exactly unsat G or unsat pi in G. Okay. All right. So good. Now, okay. So let's look at W, which is a uniformly random t-step lazy random walk. Okay, I'm letting EI denote the ith edge along this walk. Right? So, if I sampled a random walk and double checked pi bar for it, the labeling in the powered problem, you'll get it's going to be correct with probability 1 minus unsat G bar, right? It's going to be wrong with probability. So, okay. Okay, so here's what we're going to do. So for each of those indices that are really close to t over 2, this is between t over 2 minus square root t and t over 2 plus square root t, we're going to make a random variable, xi, that's going to be 1 if the two labels, the induced label that you got agrees with both endpoints, okay? And you fail the constraint. Okay, so in this random walk, as I go along the edges, particularly close to the middle, okay, we're going to look at A, do I fail this edge? And B, do the endpoints of this edge agree with, do they kind of agree with the two endpoints? Okay. Now, okay, good. So if any of these are non-zero, then you're going to kill that walk, right? So if you have an edge and your induced labels, the two letters for those vertices fail that constraint, and it's the thing assigned by the beginning and end of the walk, then in that powered problem, that walk is going to be bad. Okay, you're not going to satisfy that walk. So every time x is non-zero, you have some walk where that corresponding constraint in g to the t is failed. So that's right. So the probability that x is greater than 0 is at most unsat g to t, because every time x is greater than 0, that's some walk that failed. Yeah. Sorry? Both have to happen for xi to be 1. There's an and there. Yeah. I mean, there's implicitly an and there. Yeah. Okay. Good. So now we need to analyze the probability that x is greater than 0. Ah, jeez. Okay. Okay. Let's see what we can do. Okay. So the expected value of xi we claim is at least mu, which is unsat in G, right? So what's one way we can see this? So mu is unsat G, right? So that's the number of bad edges. So the claim is that, you know, xi, uh, the probability that xi is 1 is roughly the probability of sampling a bad edge for any edge in the middle, for any of the middle indices. Yeah. So I think this is the right direction. So this originally came from sampling a walk first and then looking at the ith edge, right? But what we could do is we can generate a walk like this, pick the ith edge first, and then walk I minus 1 steps over here and t minus I steps over there. And that will still give me a uniformly random t-step walk, right? So first, you have a probability mu of getting a bad edge, right? And I is close to the middle. So with constant probability, if you walk out, I steps and you look at the letter, it's going to match your induced letter. And if you walk t minus I steps with constant probability, it'll match your induced letter. So you lose some constant. So that's why it's big omega mu instead of just mu. So imagine generating the walk differently, which is starting from the ith edge. Okay, good. Good. Okay. So that's everything. Okay, good. That was just writing out what I said out loud. All right, so the next thing we need to do is so we want to show that the expected value x squared is at most square root t mu. So what we're going to do is now look at two of these middle indices, okay? And what we kind of want to argue is, like, if we're trying to amplify things a lot, right? So at some level, like a bad edge helps kill off a lot of good edges in the walk when we're trying to amp things up. And it gets a little bit less credit when, like, a bad edge is paired up with another bad edge. Like the walk would have been killed off anyway, so it's kind of a waste of a bad edge, right? So we want to kind of bound the probability of getting two bad edges in the walk, right? Because if you don't get two bad edges, then it's going to really help you kind of have your bad edges count for more, okay? So the claim is this thing is at most mu plus 1 minus gamma to j minus I or something, right? So if you're at like edge 100 and edge 10, so there's 10 steps in between, then it's saying, okay, the odds that 10 steps away, you get another bad edge. Is something like 1 minus gamma j minus I minus 1. So why is this? Yeah, so we can generate this as slightly different. So instead of doing a random walk and looking at the ith and j, we can just start by sampling the ith edge first, and then walking j minus I steps, seeing if it's still an f, right? So you condition, you start with a point there, right? And then you randomly walk around. So first the odds of getting in there is 1 mu, that's the first mu. And now the odds that, 10 steps later, you're again on a bad edge, in this bad region, that will go back to this lemma, which I only briefly mentioned. Okay. So that the odds that here, I steps later, but for us that will be j minus I, you're again in the mu region, will be mu plus 1 minus gamma to the j minus I, right? So what you're hoping is that if the graph is an expander, then the odds aren't, it's as if you completely sampled another edge. That would just be mu, right? So if you just sample any edge, that's mu. But it's not, if it's a completely random sample, right? And now expander is not a perfect sample, but it's close. So you're going to pay some additional cost relative to 1 minus gamma. Okay, so when gamma is bigger, you have a bigger spectral gap. That second term goes down, and it looks more and more like, oh, when your I steps away, it's just an independent sample. So independent sample will get you mu, and then you pay a little bit because it's not exactly an independent sample. Okay, good. So that's quantifying that intuition. Hopefully we have some things written. I guess so. Okay. Okay, so that's what we did. That's exactly, okay. Even a condition literally showed up, so you were correct. Okay, good. Good. Okay, making progress. Okay, now I want to show that expected value of x squared is at most square root t mu. So to this end, we just write things out like this. So this is breaking out, we're just expanding out x is the sum of xi squared. And we plug this thing in. X is the sum of xi's. And yeah, now I'm just plugging in. Okay, as we try to prove the PCP theorem in 13 minutes. Okay. All right, so good. So that's nothing too special. Okay. So maybe just to double check. So the number, we're doing indices from t over 2 minus square root t to t over 2 plus square root t. So size of I is about square root t. Okay. So mu square root t, mu squared t is actually, we assume mu is at most 1 over t, because otherwise we're basically done. Okay. And even this, okay, this looks messy, but we just bound them all by 1, and you get another size of I term. Okay. All right, good. So that's fine. Oh no, you don't bound them all by 1. You have to look a little bit more carefully. Yeah, but ultimately, because there's two summations in there. It's I and j. Okay, but it's not bad. All right. Good. We are making progress. So let's see here. Okay. All right. So ultimately what we want to do is say, okay. Okay, so here's a claim. The claim is that the probability that x is greater than 0 is at least the expected value of x squared divided by the expected value of x squared. Okay, sounds like I said the same thing twice, but one has a square inside, the other has a square outside. If that were the case and I just plugged in what we have above, then we should get square root t or something, right? Then we should get this. I think that's correct. Okay. So to do that, we need to show that the expected value of x squared is less than equal to probably x is greater than 0 times the expected value of x squared. So that's what we'll do. And then we'll be done with this important lemma. Okay, so we're going to take conditional expectations. I don't think anything's written. Yeah. We'll take conditional expectations for x given x greater than 0 squared times the probability that x is greater than 0 squared. Okay. Now, okay, I'll let you tell me why this is true. So probability that x is given, the expectation of x given x is greater than 0 squared is at most the expectation of x squared given x is greater than 0. Oh, yeah, this is Jensen's inequality, which has quietly appeared in the bottom right corner. Uh, yeah, it's like Terminator or something. Like I made these slides years ago, and I just like left little hints for myself as we reconstruct the future. Okay, good. So that works out. Um, oh, so you need a squared. So this part's kind of cute. So uh, you get if you take one of these squared terms and multiply it with this, then you get to remove the expectation. Okay, so you get one probably of x greater than 0 left over. Okay, okay, good. So I think we have shown this claim that we do ramp things up by square root t. We omitted two things that actually, if you had time and normally it's given for homework, you would be able to do. One is to show that this expander mixing lemma, which you can probably do because it's very similar to what we did a week or two ago. And the other is a binomial distribution, which is just, kind of calculations related to Chernoff, things like this. But by now, the intuition, hopefully those claims are at least intuitive by now after the semester. Okay, good. All right, so we only have one part left in 8 minutes. Okay. But actually, the great news is that this part is the sketchiest because there's one part we have to black box. Yeah, because we didn't do Fourier analysis in this class. In the past, I used to do this lecture a little bit earlier, and then we would spend a week doing Fourier analysis. But it has been made clear to me nobody likes that part of the class. So, because I don't think I'm doing it slowly enough. So I don't know. Sometimes the toolkit course does Fourier analysis more slowly. You need something called the long code. Yeah. Okay. So now powering is great because we can increase unsat quite a bit. We can even control by choosing t. Okay. But our alphabet blew up because each vertex is like, labeling the entire neighborhood. So we want to bring the alphabet back down. Okay. So this will be a composition of two steps. Okay. So it's actually kind of cool. Okay, so we're going to actually take the alphabet size to some extent in the first step from however big to 2. Okay, so step 1 is going to be, we're going to reduce the alphabet to 0, 1 by using error correcting codes. Okay, so if done more slowly, like, this lecture would just bring in everything we've ever done in this course. And then step 2 is you're going to replace, okay, so there's going to be an issue. Maybe I'll explain this first. So what we're going to be able to do in the first step, which is the first arrow, is we're going to be able to take each constraint which has many letters, okay, and we're going to use some kind of code to replace every edge with an alphabet of size 2, except the constraint's going to be over a constant number of variables. Okay, so instead of having an edge with 2 endpoints, it's going to be like a hyperedge with many endpoints. Okay, so the second step is going to replace each of these hyperedges with graphs, and that's completely black boxed. Okay, so what's the idea behind the error correcting codes? So what you can do is you can take your alphabet and replace it with a code it was roughly log of size of A bits, which is what you expect to encode size of A, right? Was relative distance rho, some constant rho. So this means that any 2 code words, so each letter, gets some bit string, right? And out of L letters, if rho is like 10%, 0.1, any 2 code words have at least 10% of letters off. Okay, so that's the distance of the code words. Okay, so that'll bring everything down to an alphabet. Okay, good. And you'll just do nearest decoder. So given a code like this, you're going to split every vertex into L vertices, where L is the length of the code. Okay, and so now you have something like on the right. So this vertex has become L individual vertices, but they're going to have just 0, 1s alphabets. And now I want to define a constraint So I want to take this constraint over two vertices, but with many possible letters, and define a constraint over sort of the 2L bits that are involved. What would be a natural way to do this? So you're given two L bit strings. Well, okay, so we want to simulate this constraint, right? So in particular, if these bits exactly encode a letter, it should just plug in the letter into the constraint. But of course, these bit strings may be kind of messy and not exactly a letter. So what we'll do, we'll take this, we'll decode a letter, and then plug it into the constraint. Okay. So, okay, so for each edge, right? Uh, oh, this vertex got split into a bunch of vertices. Each now just has a 0, 1 letter. 0, 1 letter. And I'm going to make a new constraint where, given a bunch of letters for you and a bit string for you and a bit string for V instead of letters, I'll decode, or no. I won't actually decode. If the bit string is the code for A1, and if the bit string is the code for A2, and A1 and A2 satisfy the original constraint, then I'll say yes. Okay, so I'm defining an FE that's taking two bit strings instead of two letters. And all we're saying is, let's make, if the bit strings match the code words of letters, plug that letter into the original constraint. If the bit strings are just bad, it automatically gets 0. Or if they correspond to letters that are bad, then it gets 0. All right, but what that does is at least it breaks the alphabet from big to now just bits, right? Because every letter is just 2. The only problem is that we lost the graphical part because we have this constraint that deals with a lot of stuff. Okay, here's a second black box. Okay, so this is where you need the Fourier analysis stuff. Okay, so the claim is that for every one of these edges, we can take that formula, which is really some constraint on top of this coding, and we can construct like a miniature graph CSP. Okay, so we can take that black box and replace it with a graph with these properties. So what we're kind of do is like you're going to take the two L vertices from the two bit strings, and you're going to add a few more vertices to this graph, intermediate vertices. Everything's small, and then you have some completeness. So if the two bit strings are good, then you're promised that there's a way to fill in an assignment of letters to the new intermediate vertices so that everything is satisfied in between. I know I'm going too fast, but I'm assuming you don't want to talk about this on Friday. On the other hand, if your formula is not satisfied by the bit strings, okay, you can make this graph somewhat robust in the sense that any way that you extend, you assign letters to the new intermediate vertices, you'll get some error proportional to the Hamming distance from your bad bit strings to the nearest good assignment. Because there's some assignments that are good, but they're many bits away or something, and you'll get some unsat proportional to this. Okay, good. Okay, so we want to show this thing is good. But we won't, okay. So on one hand, if you're given some label for pi that achieves some unsat, you should extend it to your new complicated version, which includes the code and includes these intermediate graph things, by just taking your letters, writing down the bit string, and then coming up with the best extension. And then if you walk through the soundness completeness, you're going to be okay. In the reverse direction, So in the reverse direction, we want to show that unsat G bar is not too much smaller than unsat G. Okay. And the idea is as follows. If you have some labeling for all the bits, okay, and you just decode it, okay, and use that to give you letters for the original one in the big alphabet. So the claim is that for every edge, if your new assignment fails the edge, this is getting silly, you're going to get most of that auxiliary graph wrong, okay, where rho is the relative distance. And if that's true, then you're going to get, am I going to, yeah, what should we do? Should I rush the next 2 minutes or should I spend 5 minutes at the beginning next time finishing this? Well, there's another class coming in 7, 8 minutes. Are you guys sure? Okay. Okay, so I want to argue that for each edge, if my labeling from decoding the bits fails that edge, then that labeling must fail at least a row fraction of that auxiliary graph CSP that was created by the black box. Okay, I just want to show where the relative distance from Hamming comes in because rho was the relative distance of the code. So if that's true, then when you look at unsat of pi bar, I can think of that as, oh, let me sample a random edge and see what unsat is on the auxiliary CSP problem that's created. Okay? And we can do that conditional on the probability of failing E. Okay? Now, the probability of failing E is unsat of pi, and unsat pi bar G should be rho. So I should have probably written a rho here, omega rho unsat GE. I think we're going too fast, but okay. Almost done. Okay, I think this is the last claim. And then there's one more slide to bring everything together. Okay, so the claim is that for each edge, if my decoded letters fail that edge, then we must fail a row fraction of the constraints in that auxiliary CSP problem that was created for that edge. Right? Because remember, the edge was transformed by the code, which made a hyperedge, and then we throw this black box, which made it a regular graph again. Okay. So, okay. So let's say that that U bar is like sort of the individual bit vertices for U, and pi U bar is that corresponding pi bar U bar is the corresponding bit string. Then pi U is coming from decoding these two strings. Okay. Now, so if our labels fail E, then I know that the distance from any good, okay, so F sub E is supposed to be any of the good letters, the codes of the good letters. It must be kind of far. Okay, because you have some letters that are bad. And at least one of them are bad. So to get to two good letters, you're going to have to, one of these codes is going to have to change by a lot of, one of these codes will have to change by a lot of bits. Okay. So, good. And so if those labels if those bit strings are very far from anything that corresponds to good letters, then our black box ensured that you're going to fail some proportional fraction of the constraints in that auxiliary graph CSP. Okay, so that's where soundness comes in. So somewhere it's important that if you're not encoding the right letters, then you must have many bits that are wrong. And then you can get this thing. Okay. All right, I think it's mostly just about the connection, knowing that error correcting codes entered this proof at some point. Okay. Okay, so those are kind of the three steps. Obviously, we rushed a third. And whatever I said was 5 minutes is already passed. So if you bring everything together, right, the three steps, okay, the degrees, you take an arbitrary degree, make it constant, it gets ramped up by powering, and then the alphabet reduction just throws it into no one knows what it becomes, but then it's okay because next time around you bring it down to a constant. You can handle any input degree. The spectral gap, you can always fix it, and even though it gets messed up by alphabet reduction, you'll be able to fix it next time. Okay? You need the mixing property to be good because of the conjunction thing. Now the real thing is unsat. So if you start at some value alpha, you lose a little bit in expander, some constant. You lose a little bit by constant, but then you ramp up by square root t, and then you lose another constant. So you need to make square root t big enough to outdo all the constants, so that's a constant. And then the alphabet size doesn't change initially. It goes crazy, but then you bring it back down by using this error correcting codes combined with this black box. Okay, so I didn't do great justice to the last part of it, of course, for lack of time. There's only so much you can do in 15-minute lectures, but those are the high-level ideas. So you guys will probably be, have plenty to study already, but maybe someday you'll come back and revisit these notes because there's something profound going on. So Friday, we'll just do the same thing where you can ask me any question you want. Okay, and we'll just hang out on the Blackboard. Okay, thank you.